Afternoon, nerds. Whee! Okay. Today we are going to start transformations. Now, hopefully you remember some stuff about transformations from Algebra 1, but I'm going to teach it as if you have never seen it before. And that's because I am the greatest. I'm the best at teaching this material as far as I'm concerned. Transformations are super important, and because of that, I try to make sure that they're very easy for the students. I'll take my time getting through it. That's why it's going to take me a total of 3 days to get through it. And at times it might seem like I'm going unnecessarily slow. But trust me when I say there's a method, there's a process, and if you follow it, you're always going to be good at transformations. Okay? First thing that we're going to talk about with transformations is function notation. What you're looking at right there, f of x. This is function notation. We need to talk about this because all transformational rules are given to you using function notation. All of these rules are all from function notation. I just need you to understand what it is you're looking at. So recall, please, that f of x is a fancy way of saying your y values. So anything that changes on the outside of this f of x structure is a y change. That's you literally changing the y values. That's happening outside of the structure. And if you make a change inside the structure, this is not a y change. That's you literally changing the x's. So I will typically refer to these things as inside changes and outside changes. So here we have inside changes, and here we have outside changes. The nice thing about transformations and function notation is regardless of what the function is, transformations will affect every function you can think of the exact same way. So you don't even need to know what a graph looks like to know what kind of transformation is going to occur to it based on the function notation rules. The easiest ones to work with are translations, and that's why we start here in translation land. Translation means the same thing it meant in geometry and Algebra 1. It means a shift, and you have 4 directions that you can shift. It's all 4 fingers. There you go. You have 4 directions that you can shift: up, down, left, or right. Okay. The y-axis is the axis that's up and down. I need you to know the vocabulary word for that is vertical. You need to know that vertical means up and down. Here, I have outside changes occurring. And since f of x means the y values, these are y changes. These transformations are literally changing the y values. This one says, take your y values and add a number to them. If you add a number to y's on the y-axis, you're going up. And that's exactly what this does. It'll shift you up however many units that is. And this says y values minus a number. If you take your y values and subtract a number, typically you're going down. And that's exactly what they do. So it's nice. The y changes do exactly what they look like they're doing. You just need to know that anytime, anywhere, either in the structure or out of the structure, you see addition and subtraction, that is a shift. So all addition subtraction with function notation rules is shifting. You just need to know which direction. And the y values do exactly what we think they should do. So they have, I like to say, same effect as what they look like. This is the same effect. It looks like it goes up, it does. It looks like it goes down, it does. Cool beans? So if I ask a student, okay, that transformation is inside or outside, and they say outside, and I say, does that change the x's or the y's? And they would say y. I say, vocabulary, is that horizontal or vertical? And they would say vertical. And then I would say, same effect or the opposite of what we think it should be, and the y values are same effect. These are inside changes. Inside changes are you directly affecting the x values. They're changing the x's. the x-axis is horizontal. So anytime you make a change on the inside of the function notation, this is a horizontal transformation. Okay. But unfortunately, these things, they do the exact opposite of what they look like they do. So here is you subtracting from your x values. You think that should go left. It doesn't, it goes right. And here's you adding numbers to your x values. You think that should go right. It doesn't, it goes left. But I do have a fun way of remembering that the x changes are the opposite. You guys ready? Okay. So, has anybody in the room ever had to dump somebody before? Okay, I got some liars in the room because I know there's some heartbreakers in here. Well, what's that, Brody?
No, I don't talk to females.
He doesn't talk to females. Don't worry, in a couple years, you won't think they're icky anymore. So anyway, anyway. Oh, so it's just me. Okay, well, anyway, let's just pretend everybody in the room has had to, unfortunately, break a heart before. What I would say is there's probably a reason why you dumped them. There's a reason why you chose them to be your ex, and it's because the exes don't do what we want them to do. They typically do the opposite of what we want. And that's why there are exes. See, works pretty well, doesn't it? And even better than that, do you know what you do after you after you dump somebody? You replace them. You substitute, you replace them. So anytime you are forced to make an inside change, your job is to replace your ex with something new, which I'll get into more down below. I already said that all of these are function notations. These are the function notation rules for shifting. There. So once again, anytime you have adding and subtracting, doesn't matter where it occurs, inside or outside, that's a shift. Outside changes, change the y's. The y's are vertical, and they do exactly what we think they should. So you see plus, yeah, that means up. Inside changes, that's you changing your x's. X changes are horizontal, and there are x's because they do the opposite of what we think they should. You see plus, that means go left. Cool? All right. So the examples down below are asking you a very simple question. Now I'm going to take it up several notches from what the directions are asking because I'm trying to really drive home a concept here. When you go to do your homework, you just do the one thing it asks you to do. You don't have to do any of the extra stuff that I'm about to do. But all the extra stuff that I'm doing is going to make transformations much, much clearer for you. First of all, I'm not going to say y equals x squared. Instead, what I'm going to say is f of x equals x squared, because we are going to be using our function notations. This literally says my y values come from squaring the x value. This is what this says. And to drive this home really, really well, I'm also going to pick a point that exists on this function, and I'm going to show you how the transformation affects the coordinates as well, because here's the dirty little secret. You ready? You've been lied to. Transformations don't transform graphs. They transform coordinates. X changes, change x values. Y changes, change y values. And when you connect the dots, you'll have a new graph. There's not a single transformation in algebra that affects the x's and the y's. They either affect the x's or they affect the y's, never both. That's why we don't do rotations in algebra. Okay, like I said, I'm just going to pull a random point off of this function. Not something you have to do in your homework. I'm just making really good notes. I need someone to shout out a single number. A small, what? Okay.
0.
Oh boy. Okay, our number, 4 is a much better number. Ones and zeros. The reason why I don't do ones and zeros is because ones and zeros do, when you square them, you can't tell anything has happened. But 4 is fine. So we're going to pick a random x value of 4. And if we square that x value, we get 16. So what we know is that one of an infinite number of points on that graph is 4, 16. Could have been any number. But we say 4. Not ones and zeros because they do dangerous things with squaring. But there we go. All right. Well, do I have a brave volunteer that wouldn't mind answering a string of simple questions for me? I'm trying to learn some names. Okay. And I know your name when I'm doing attendance, and then I forget when I'm not. What's your name? Jake. That's right. Okay, Jake, you ready for these questions?
Yeah.
All right. You could see this, and you could see this. What I'm going to ask you is, this minus 4, is it inside or outside of a structure? Look. Compare the two. If you had to say one of these was happening inside something, which one is it?
Outside.
This is outside. Yes. This is an inside change. When we say inside changes, we mean literally changes where the x was. This is not you changing where the x was. The x is literally underneath an exponent. Okay. So outside change. Since it's an outside change, am I changing my x's or my y's?
You're changing your y's?
Changing your y's. Yep. See how they say your function plus or minus a number?
Yeah.
This is my function. There's my f of x. So this is my y values are x squared. This is my y values minus 4. So we have an outside change, which means I'm affecting my y's. The vocabulary for y's, is that vertical or horizontal?
Vertical?
Yes, it is vertical. One way of remembering that horizontal side to side is the horizon goes side to side. That's why it's named the horizon, actually. It's after the word horizontal. Okay, so we're talking about a vertical change. Last simple question for you. Since it's a y change, vertical change, and it's outside, does this have the same effect or the opposite effect as what it looks like?
Same effect.
Jake, same effect. Now, Brock, since you've volunteered, thank you, Jake. Brock, we know that this is the same effect as what we expect. So if you had to describe these transformations in words, what would you say this does to the graph of x squared?
It brings the whole thing down, every single point down 4 points.
There we go. So to keep life easy, what we're going to say is shift down 4 units. So does it seem like I needed to go through all those questions? No. But I'm telling you, you want to go through that tiny list of questions for yourself every time you do one of these. It's going to make you very good with transformations. Shift down 4 units. Do I have another brave volunteer that thinks they could give me the function notation rule for shift down 4 units? Okay, Brody? Well, that's what it is, but I want one of these. Can you give me the rule for it? Like, which one is shifting down? Right? But instead of saying C, we're going to say 4. There you go. So our rule is f of x minus 4. Now wait, before you go writing that, can we agree that moving a graph down 4 is a new graph? It's a different thing? Okay. So since it's a different thing, I want to give it its own name. I want to say that g of x is what you get when you take your f of x and subtract 4. You might be wondering why we give it a new name. Well, let's see. Sebastian. What's mom's name? Tanya. Would you prefer that we called you Tanya's kid or Sebastian? Of course you would. You see what this says? This is the description Tanya's kid. This is the name Sebastian. This is the description of how you got to here. You guys cool with that idea? It shows you that you altered f of x. How? That's how. And this is what you now name it. All right? Basically, when you transform a function, you have to change its letter. It doesn't matter what letter you choose. We typically go in alphabetic order. Okay. And just to really drive it home, I want to show you how this transformation changes the coordinate that we said was on f of x. We said take 4 away from the y's. You literally just subtract 4 from the y's. I picked a random coordinate, 4, 16. That is on f of x equals x squared. But if you shift the whole thing down 4, this point gets shifted down 4 to 4, 12. Transformations don't change graphs, they change coordinates. Okay? Awesome. New color. Do I have another brave volunteer to run through the string of questions with me on this? He's pointing at Trent. You've been volunteered, Trent. Okay. Trent, would you say this is an inside change or an outside change?
Inside.
Inside, I 100% agree. Since it's inside the structure, am I changing the x's or the y's?
X.
X's, awesome. And for vocabulary purposes, when you change your x's, is that a vertical or a horizontal change?
Horizontal.
Horizontal, just like the horizon. So we know we have a horizontal something or other. Since it's addition and subtraction, we already know that it's the same kind of transformation that we were dealing with here. It's a shift. So all addition and subtractions will be shifts. My question for you is, same effect or opposite effect, since it's inside? Opposite effect. So it looks like it's what? What does it look like it's doing?
Going down.
Well, the x's are left and right. So it looks like it's,
Oh, my bad. Going right.
what's it look like it's doing?
Well, it looks like it's going right, but it is going right. Wait, is it right?
No, you said it backwards.
Alright, I'm backwards.
It looks like it's going. It is going to the right. He's killing me. I'm trying to get him. It looks like it's going to the left, but since it's the opposite of what we wanted to do, this is going to the right. So we would say, he was so close. So we would say, shift right 3 units. The problem was he was trying to jump to the answer instead of why it's the answer. Shift right 3 units. Thank you for playing my game. Now, I need another brave volunteer then that can tell me what the function notation rule is then for shift right 3 units. And I'll go ahead and get you started. We're going to rename this thing. I've already used f, I've used g. Well, this one will be h of x. So we'll say h of x is, Ilya, what do you got for me?
F of x inside parentheses.
Mm-hmm.
-3.
Where's the minus 3?
Inside.
Inside, yes. But remember, we're replacing this x, right? So we're not just going to write the x in black. And you might be saying, what's the difference? What I'm trying to show you is where there used to be an x, now there is an x minus 3. I'm literally changing everything that was in the parentheses. I'm not just saying write a minus 3 after your x's. That is dangerous. Why, Mr. M? I don't see the difference. Oh, allow me to show you the difference. This is what happens when you just write a minus 3 after your x. This is how you replace your x with an x minus 3. This is shift right 3 units. This is shift down 3 units. And it matters because of distributions. So whenever you're writing your function notation stuff, anytime you change the inside of the parentheses, you replace every x with what is now in the parentheses. So do you remember when I had you testing for even and odd functions by plugging in negative x's, and I said you're replacing every x with a set of parentheses? Anytime you replace an x, you replace the whole x, just like you would with that old boyfriend or girlfriend. You don't keep pieces of them on the side. No, your side pieces are gone. You got yourself a new person now, okay? All of x has been replaced. And just to really drive home the concept, we knew that 4, 16 was on our graph. But we said shift to the right 3 units. If you go to the right on a number line, are your x's getting smaller or bigger? They're getting bigger. Shifting right is you adding 3. I know it looks like you're subtracting 3. You're not. You're adding 3. So the new coordinate is 7, 16. Like that. Are there any questions for me on what I'm doing, how I'm doing, why I'm writing things the way I'm writing them, anything? On your homework, the first 3 questions just want you to describe the transformation. So it's just going to be the word description. That's it. If you want to go over and above to really test your abilities, describe the transformation and write a function notation rule for it. But all I'm asking for in the homework is this description. I will tell you on your test, you need to be able to move between the function notation rules and the descriptions. You need to be able to move between these two on the tests, okay? As well as get new equations, as well as get new graphs, things like that. Everybody's cool in the gang on this? No? No questions out there, huh? Okay. It's my quiet class. One of the things that I really like about transformations, and I already mentioned this, but I really like the fact that they change all functions the same way. I can invent a function that you've never heard of before and then say, what do you think f of x minus 4 does? And you would go, well, whatever that graph is, it shifts it down 4. And I go, exactly. That's what's great about them. They do a lot of stuff for us. They tell us what to expect without even looking at a graph. Oh, I expect to see something that has had this done to it. All 3 of these examples start with the parent function f of x equals x to the 3rd. It's the dotted one on all 3 of them. And regardless of whether or not you've ever seen a cubic graph before, there they are, we should be able to just see, what did we do to the dotted graph to get to the solid graph? We should be able to see that. And what we're going to do here is we're going to describe what had to be done to the dotted graph to get the solid graph in words. Getting a word description. We will then get a function notation rule for that description, and we will then use that description to get the new equation. Whereas in these examples, you had the new equation. In these examples, we are getting the new equation. Okay? All right. I need a brave volunteer to tell me what I would have to do to this dotted graph to get to the solid graph. I could find unwilling victims, or I could call on brave volunteers. You guys are really going to make me pick people, huh? Okay. I'm trying to remember your name. Don't say it. I know your name. I do. I forgot it, though. What's your name? Thomas. I knew it started with a T, and all I could think of was Trent. Sorry.
This is Trent.
I know, but you laughed and looked at me, so I looked at you. Anyway, Thomas, what would I need to do to the dotted graph to get to the solid one?
Wait, I'm trying to get the dotted line onto the solid.
We're going to make this dotted one become the solid one. What would I have to do to this dotted one?
You have to shift it down by 3.
Shift down 3 units. Sounds good to me. Here's a color I haven't used yet. Perfect. Shift down 3 units. That is the verbal description. Now I need somebody else that could turn that shift down 3 units description into a function notation rule. We will call this one g of x. Okay. Daniel Q. What would be the function notation rule for shift down 3 units? On the outside, I like how you said that. Yep. See, because this is a vertical change, a vertical shift, technically we're supposed to say vertical translation down 3 units. Shift down 3 units is good enough for me. Because it's a vertical change, it's a y change. And because it's a y change, it happens on the outside. And outside changes do exactly what we think they should. So there's you doing the -3. I changed colors like this for a reason. You guys know from Algebra 1, whatever you do to one side of an equation, you do to the other, right? Okay, watch this. I'm writing my f of x. I'm going to leave a space, equals x to the third. So there's f of x equals x to the third. The function notation rule said subtract a 3 from f of x. But if I subtract a 3 from the left side of the equation, I have to subtract a 3 from the right side of the equation. And I think it's plainly obvious that the black graph is not the same as the dotted graph. So it needs a new name. Here's its description. Here's its name. G of x is x to the third minus 3. Just like that. It seems all elementary, and it seems like I'm doing too much. Trust me when I say I'm trying to get you through with the baby steps. That way, when you have to do the monster steps on your own, you think it's easy. Is there anybody that wants to ask me anything about what's happened on that question? No? Easy? Okay. Alrighty. Brand new volunteers, I hope. Someone tell me, what do I have to do to this dotted equation, this dotted graph, I should say, to get to the solid graph? Barry, what do you got for me?
Shift left 2 units.
Shift left 2 units. Works for me. Bless you. Shift left 2 units. Awesome. Thank you so much. While I got you on the line here, shifting left, is that horizontal or vertical?
Horizontal.
Horizontal, and since it's horizontal, is it changing the x's or the y's?
X.
So where would I see that transformation, inside or outside?
Inside.
Inside. Awesome. So we know we're dealing with a horizontal translation, left 2 units, and we know that because it's a horizontal transformation, we know that it's happening inside the function notation. One last question, Barry.
Yeah.
Same or opposite?
What?
Same effect or opposite effect is what we expect from the x's?
Opposite?
Opposite. They're x's for a reason, right? Because they do the opposite of what we want. Okay. So hearing all of that stuff, is there somebody out there that can give me the function notation rule that we are going to use to define h of x? Ilya?
G of x is equal to f in parentheses x plus 2.
Sounds good to me. I'm going to call it h of x, though, if you don't mind. But yep, x plus 2 in parentheses is exactly what we should see. Perfect. I'm going to call it h just because it's not the same as the g graph. Again, the letter is just, since I called this one g, I don't want to call this one g. I'm bad with names anyway, so I'm going to try and make them as different as possible. Cool. So here's how this works. You take your equation, which was f of x equals x cubed, and everywhere there was an x, there's now a set of parentheses. Those parentheses are being filled with x plus 2. If you do it on the left, you better do it on the right. And by the way, this is its description. This is its name. And it's finished. You see, I should be able to shift these things in 2 different directions, and you should still be able to pull this off. Because no x changes change the y's, and no y changes change the x. So you could have transformations happening on the inside and transformations happening on the outside at the same time, and they would not affect one another. How are we feeling about this so far? Not too bad, right? Not too bad. Okay. Then I need one last brave volunteer to help me out with this last one. It's always a guy. Where are my gals at? Where are we at? Ladies, come on. Somebody talk to me. Please. It's just like high school again. Girls won't talk to me. Ba-dum-bum. Good God. No? Nobody? Oh, thank you so much. I forgot your name though. What's your name? Sophia, thank you. Sophia, what would you do to this graph to make it become this graph?
Shift to the right 3 units.
Sounds good to me. Shift right 3 units. Thank you so much. While I have you on the line, if you are shifting to the right, is that going to be a vertical change or horizontal change? Horizontal, perfect. Is that going to change the x's or the y's? X's, good. Would I see that transformation on the inside or the outside then? Inside. And would that effect be the same or opposite of what I expected? Awesome. Sophia, killing it. Okay. Do I have the next brave volunteer then? That'll give me the function notation rule for shift right 3 units. We're so close. Come on, guys. It's the last one. Man. All right, Ryan. You're the victim.
What letter do you want to use?
I don't know. Pick a letter. Pick a letter. I don't care.
I have X.
I have X. All right.
This was F, parentheses, X minus 3.
Good. Oops, that's not blue. That's green. Ah. I don't know why everybody's so nervous. We just did that one. Look, it's right there. That one was free. Thanks, Ryan. F of x minus 3 in parentheses. So wherever we had an F, or excuse me, an X, we throw a set of parentheses. We fill those parentheses with x minus 3 on the left side. So we fill them with x minus 3 on the right side. This is its description. Ryan chose the letter I. Oh, I wrote that in black. Look at me. It's supposed to be blue. The very end, my pattern's going to fall apart. Made it so far. And there it is. Questions, comments, concerns, anything I can clear up for you with transformations, vertical, horizontal, inside, outside, any of that stuff? You sure? Maybe I'm just so good that no one ever needs to ask any questions. Maybe that's what it is. Or you know what? Maybe it is that you're all just nerds. Thanks, guys.